Hello, good afternoon, everyone. I'm Rajeshree Liya from Ahmedabad University, India, and I'm working with Professor Aditya Singhal. So, my research area is to develop the catalyst for the oxygen evolution reaction, which is a part of the water splitting reaction. And today, I'm presenting one of my work, which is the platinum incorporated NiFe2O4 for the oxygen evolution reaction. So these are the outline of my presentation. So the due to the depletion of fossil fuels and they are also connected with environmental issues, high population growth, and economical developments are the major reasons for the global energy crisis. So people are moving towards utilization of the renewable energy sources. So what the problem happened with renewable energy sources is that they are intermittent. So if we want to utilize the 100% renewable energy sources energy, we can develop and we should develop technologies of energy conversion, storage, and utilization. So the hydrogen economy, or we can say hydrogen, we can use as a fuel and as an energy carrier. We can convert the renewable energy into the hydrogen as a storage energy, and we can utilize those hydrogen fuel whenever it is in use. So in if we want to get a hydrogen, it requires the high temperature of 3000 degrees Celsius. Sorry. So if we required a hydrogen from water, where it requires 3000 degrees Celsius temperature, as hot as sun, but we can do the same reaction. We can do the same reaction at the room temperature using the electrochemistry. So these are the setup of 3 electrode system from electrochemistry. From this kind of electrode system, we can get hydrogen and oxygen at a room temperature from water. So then why the need of oxygen evolution reaction catalyst? So this water splitting reaction is a very complex reaction because it is connecting with the 4 electron transfer, and it has a high over potential. So the standard potential of the reaction is 1.23 volt, but when we perform the same reaction at a laboratory scale, it performed at the higher over potential. So we wanted to decrease this potential, and also specifically the oxygen evolution reaction has these 3 intermediates, and it requires very high over potential energy. So we wanted to develop the catalyst for this reaction. Then we can utilize it in the electrolyzer, and we can get a good yield, good product from the electrolyzers reaction. And we can utilize this also in the fuel cell, regenerative fuel cells, zinc air batteries also. So specifically to incorporate this reaction, the noble metal oxides are very useful, but they are the noble metal oxides are a state of art oxides, but they are very costly and less abundant. Another option is the transition metal oxides, but what happens with transition metal oxide, they are not that much of efficient. But what we are doing is that we are utilizing a very less amount of noble metal into the transition metal oxide to get a good activity. So what happens if we are using a whole noble metal, it is costly. And if we are using a transition metal, they are not that much of costly and abundant, but they are not giving good result. So if we are using a very less amount of noble metal and incorporate them in the transition metal, and if they are giving good result in our reaction, that would be more good. So this nickel iron oxide, the spinel is a very not moderate, it gives very moderate oxygen evolution activity, but we incorporated platinum in this spinel. So first of all, we have synthesized this NiFe2O4 using the solution conversion method and perform the XRD and CV. From this CV, we can get the current density value and we can get idea how much the catalyst is active or not. And we got a pure compound. Then we substitute 0.25, 0.5 and 1% of platinum in this matrix using the solution conversion method. And we got this CV, cyclic voltammetry study. And surprisingly, we got that the activity of platinum incorporated compound have a less current density. So it is not like that. People are every time say that if we incorporating noble metal into compounds and they are giving good result. It is not happen like that. Actually, if we are dealing with those things, we get idea about that. It is not happening every time. We have to optimize the things. We have to deal with other parameters also. So also we did the this platinum supported NiFe2O4. We synthesized them using the formaldehyde reduction method. So we, in first case, we doping the platinum. And in second case, we are supporting like this NiFe2O4 we use as a support and we are dispersing platinum particle into it. So this is two different systems. And in this system also we are getting that platinum incorporated compound is giving less activity. So now what? We wanted to deep dive into this. We wanted to explore this system, why this is happening. So also we have checked the stability. This is the chronoamperometry data to check the stability of the compound. In that also, the platinum incorporated compound giving not good result. So we wanted to explore this compound, why this is happening.
But now I think it's okay. Yeah. Thank you so much. Yeah, can take this. Yeah.
So so what we did is that we used the pre-treatments, the electrochemical reduction activation. So okay. we perform the chronoamperometry data. Okay, so we perform the reduction treatments. There are lots of pre-treatment, but we chose this because we wanted to get idea about the whole phenomena.
Yeah.
So we utilize these reduction pre-treatments and we perform the negative potential chronoamperometry. So in that particular in this particular chronoamperometry, if we perform it, then what happened? The catalyst become reconstructed. Some active site could be generated. Some oxygen vacancies could be generated. So we wanted to deep dive in this and we performed the chronoamperometry at negative potential. So it is very important in this reaction if there is an active site or if there is some defect, oxygen vacancy, then the procedure can be happen at lower potential. So we after performing the negative potential chronoamperometry, we studied the OER reaction and we get that in case of substituted compound, 2.5% is giving good result, which is 11-fold increment compared to the parent compound NiFe2O4. And in case of supported compound, we are giving 15-fold increment in the current density value compared to the parent one. So like if you say that the only this reduction treatment is giving good result, no, it is not happen like that. If we see the current density value of the NiFe2O4 is decreased compared to the pristine one. So the activity is the good activity we can get from the incorporation of platinum and this reduction treatment, both combinedly. In case of pure NiFe2O4, the current density value is decreased after the reduction treatment. So we have also performed the chronoamperometry to check the stability and activity. The 0.25% of substituted and 1% of platinum supported compound giving good result and good stability. This is the good accordance with further study. Here also the after reduction treatment, the pristine one is not giving good result. These are the TAM images of the compound. If we see the substituted compound, there is no any specific particle of platinum is observed. So there is a successful substitution happened. And in case of 1% of platinum supported compound, a very small platinum particle is dispersed on the cluster of NiFe2O4. And this element images, we can see all the elements are homogeneously dispersed. So we have studied the pristine ERA, after ERA and after OER XPS studies. So what happened if we are substituting platinum at Ni nickel site? So platinum is in +4 oxidation state, and we are substituting higher oxidation state metal into the lower oxidation state metal. So the stoichiometry is different and the defect could be generated. So in this lattice, some vacancies could be generated. What we observed from XPS analysis. So specifically, if we see the oxygen XPS, specifically this B peak is denote the oxygen vacancies in hydroxyl group. This is very crucial for the reaction. Intensity of this peak is increased after the reduction, which shows that more this oxygen vacancies in hydroxyl group is generated, which is leading the reaction. So in case of 1% platinum supported compound, here the variety of platinum oxidation state is observed. In case of platinum XPS, here platinum 0, platinum metal, platinum +2 and platinum +4. This variety of oxidation state was observed. If there is a lots of oxidation state, it could lead oxygen evolution reaction more visibly. And specifically when we are dispersing material on the metal oxides, here the metal support interaction phenomena is occurring. So actually what happening, this support is transferring the charge or electron to this platinum surface, which is favored the reaction. So here the active catalyst is the platinum, and NiFe2O4 is giving a support for performing that particular reaction. And here also in XPS, oxygen vacancies and hydroxyl group intensity increased drastically. So also we have performed the gas analysis study. We have quantified the amount of gas evolved. So actually we are performing this study in this kind of 3 electrode system, where we use the reference as a AgAgCl electrode. For the working electrode, we use the glassy carbon, and we deposited our slurry, our active material on it, and we use platinum as a reference electrode. We use the KOH as an electrolyte and perform the electrochemical studies. And then getting a good result, we wanted to quantify the evolved amount of gas. So what we did is that we took airtight container and purged nitrogen gas for a half an hour to make the environment inert. And then after performed our studies, whatever the electrochemical studies we are performing to make the reaction feasible. And after that particular 30 minutes chronoamperometry, we took injection of that gas and we checked it in the gas chromatography, TCD detector, and we got the area from the gas chromatography. And from that gas chromatography, whatever the area we are getting, we can get the calculated moles of oxygen gas, which is evolved from this formula. So we took here a standard also. In that standard, the 1% of oxygen is there. That is a standard. We are not making it. We got it from other standard companies, and we perform the gas chromatography of that particular sample, and we get moles of it also. So we can like using these formulas, we can get moles of oxygen gas, which is evolved in our reaction. And also we can get the Faraday efficiency from those moles. And specifically in these two cases, we observe that the Faraday efficiency is more, which is a good occurrence with the whole study. Like we are actually getting the good result in this case. So these are the conclusion. Like we have synthesized the substituted and supporting material using the solution combustion and formaldehyde method. We have characterized them detailed. That is a very important that the parent nickel NiFe2O4 after the reduction treatment, the current density was decreased. So it is not happened like that only the reduction treatment is giving us a good result. The incorporation of platinum and reduction treatment combinedly giving a good result. And we also deep dive in the XPS studies also, which shows the good and significant increment in the intensity of the oxygen adsorb oxygen vacancies, and hydroxyl group intensity is more. And also from Faraday efficiency that giving a good result for these two compound. And I would like to acknowledge my university professor and the conference team. Thank you.